Hello, and welcome to this Making Stuff demonstration on ferrofluids. Making Stuff is a spin-off of the Nova series starring David Pogue that deals with material science. Material science is a multidisciplinary study of the properties of materials that includes applications from engineering, chemistry, physics, math, nanoscience, and more. This demonstration shows how material science helps to make stuff smarter. A smart material is something that can sense a change and respond to it in a way that makes it very useful. One example of a smart material is a ferrofluid. A ferrofluid is a fluid that is ferromagnetic, meaning that it is attracted to magnets.
When the ferrofluid is poured onto this large bolt, we see it travel down the treads. Ferrofluid will naturally align itself to the magnetic fields of whatever object it comes in contact with.
Ferrofluid contains iron oxide particles, which are attracted to the magnets. The spikes are formed by the complex interaction of several forces. The ferrofluid is attracted to the magnetic field, and the magnetic field is attracted to the ferrofluid as they steer each other into concentrated columns. Gravity tries to pull the columns back down, and surface tension in the oil causes each column to pull in on itself, forming the sharp tips.
Okay, so why do we call it a ferrofluid? Well, it's because it's a ferrous metal. Ferrous meaning iron. If you take a look on the periodic table, the symbol for iron is Fe. Thus comes the word ferrous for the symbol Fe. When you look at the periodic table, you can see that the materials that are in a column have similar properties. For example, take a look at 29, 47, and 79. These are copper, silver, and gold. To keep it simple, they are all soft metals and sit in the same column.
So the interesting thing about this is that it's very responsive to a magnetic field. And it's a lot like oobleck. Take the spoon and scrape around in there.
Okay. Oh man, that is unbelievable. It's cement.
So now scoop some of that up and just take it out of the magnetic field by lifting it up.
Oh, no way. This is like X-Men stuff. So it's a magnetic liquid.
We call this magnetorheological fluid.
You got a shorter nickname?
MR.
MR fluid? Can I call it Mr. Fluid?
No.
A typical MR fluid consists of tiny iron particles suspended in a fluid like oil. Without a magnetic field, the liquid flows freely. But add a magnetic field, and the metal particles line up, increasing the fluid's thickness.
Drag it up. See that? See how that's solid? It becomes solid. You're able to move it around. You take away the magnet. It returns to a liquid and flows back down again.
Now let's see how a neodymium magnet affects ferrofluid when it's suspended in water. I'm going to start by pouring the ferrofluid into the water. You'll notice that as it hits the water, it beads up just like regular oil would if poured in water. But when I place the neodymium magnet to the side of the jar, it's going to instantly attract all the ferrofluid within range. Once we add the ferrofluid to the water, it's free to travel all over the jar, which gives us some really cool effects when we pull the magnet to it. For some reason, this makes me think of Spider-Man. Not sure why. Now, I was mentioning the periodic table of the elements before. The bottom two rows of the periodic table consist of rare earth metals. We actually find that neodymium is labeled number 60 and falls into those bottom two rows. This is why neodymium magnets are sometimes referred to as rare earth magnets. They get that name because they're made up of rare earth materials, as we've just seen here. Right now, they're the strongest permanent magnets in the world.
Ferrofluids have many applications.
You'll find them in speakers, motors, even hard drives.
In devices like shock absorbers.
And then there's another suspension that's larger, and that's for really heavy-duty vehicles.
Heavy-duty vehicles like Humvees. Out here in the woods, I'm going to see just what kind of a difference using a smart material can make in a Humvee's performance. A typical shock absorber is built around a piston filled with oil. When the piston moves down, it forces the oil from one chamber to another through small holes. The thickness of the oil and the size of the holes determine how much force that takes. If neither varies, the shock is a one-size-fits-all dampening solution. No matter how bumpy the road is.
How do you make this seat recline anyway? Oh my God. That was pretty bouncy. You should sell tickets to this thing.
For round 2, the Humvee gets the smart shock absorbers. They also use a piston design, but they add MR fluid full of iron particles and an electromagnet where the fluid flows through the holes. A computer controls the electromagnet in real time, varying the viscosity of the MR fluid. This system adjusts how much force is needed to move the piston in response to the bumpiness of the road. That makes the shock absorber tunable. It can react nearly instantaneously to different size vibrations. And that's very smart.
Oh, this is nothing. How do I adjust the AC? So, you're telling me that was the exact same speed?
Exact same speed.
Well, I can tell you, if I were a soldier, I'd vote for these shock absorbers.
Oh yeah, you can see why that's a huge difference for those guys if they have to travel 25 miles in that, and the vehicles will last longer. Don't forget your seatbelt.
It can form an amazing airtight seal around a spinning motor shaft. Ferrofluid is also used to cool down the overheated wires that move inside a loudspeaker.
Engineers see a big future for them in bridge construction to squelch vibrations caused by wind and bad weather. And even for use in buildings to counteract the awesome power of earthquakes, like a steadying hand.
Ferrofluids are used in spinning objects such as in computer hard drives and in car brakes to reduce friction. Ferrofluids are also used in speakers to improve the sound quality by removing unwanted resonances. NASA has experimented with using ferrofluids to control the flight of aircraft. The ferromagnetic particles in real ferrofluid are on the nanoscale size, meaning that they are between 1 to 100 nanometers in size. 1 nanometer is 1/1000th of a meter. The ferromagnetic particles in our ferrofluid are on macroscale size. The iron filings are easily visible with the naked eye. As part of our demonstration, we made a jar of fluid similar to ferrofluid by mixing corn oil with iron filings. Although our mixture has similar properties as ferrofluid, it is not real ferrofluid. Real ferrofluids also include a substance called a surfactant that prevents the particles from clumping.
That's active on the surface between the oil and every magnetic speck. One end of the surfactant molecule grips onto the iron oxide, and the other end grips onto the oil. When they're completely surrounded with surfactant, the particles aren't able to clump together. And each particle has a lot of oil attached, so wherever the iron oxide goes, the oil has to follow.
The Making Stuff outreach program, supported by NOVA, Yale University, Southern Connecticut State University, Material Research Society, and the National Science Foundation, is meant to interest families and kids in material science.
And just as a little bonus for sticking around so long, I'm going to actually drink some ferrofluid and see what happens. Remember, if you drink this stuff, it's probably going to cause encopresis, which regardless of how cool that sounds, it's not a superpower. It might also kill you. Anyways, see you next time.
Science is so mad.
And flip! And flip! And move!
Attention right here. Want attention?
Yes, no.
And video camera.
And flip! And flip! Okay.
What's the first attraction? Would you really like to know?
Yes!
What's the first attraction? It's a magnet.
And that's ferrofluid. It takes a lot of physics and chemistry to understand how it works.